Let's look at some level 1 samples for the SQL challenge. My baseline starting out is 482 logical reads, and the first thing I'm going to do is attempt to index what might look like an equality predicate in here. When we think about indexing, a lot of the advice that we'll see on the internet is to look in the predicates of a query and look for equality comparisons, where we're looking for a column to be a specific value. Because if I have a column and I'm looking for a specific value in it, and I put that in the key of my index, I can seek right to that value. And we do have an equals sign here, but this is not an ordinary equality predicate, because I'm not saying first report year equals 1989. I'm saying first report year equals another column. First report year and last report year, they could be any year from 1880 to 2017. I don't know. For any given name, is the first report year equal to the last report year? Well, let's see how well that can be indexed with a regular row store non-clustered index. So what we're going to do first off is we're going to try to follow that advice. We're going to treat this like an equality column, and we're going to create an index where our first key columns are first report year and last report year. We are then also going to add total name count descending to the index. That is what we're ordering by, and we also have a predicate on total name count is greater than or equal to 10. Finally, we're going to put first name as an included column to cover the query with the index. We have now specified all of the columns this query is pulling from this table. We have specified them in our non-clustered index so that SQL Server won't have to go look up a column from the clustered primary key or anywhere else. It'll have everything it needs for this query. We're making this index look as attractive as possible. Let's create this index, which in theory, and I am in the wrong database to create this index. I need to use the database that I restored there. So now that I have restored the database, I can create the index on this table with what may be an equality comparison here. It is an equality comparison in our query, but is it seekable in our non-clustered index? First up, we are going to measure the logical reads for our query, and our logical reads for the query come out at 448. Well, 482 was my baseline. We're coming out at 448 now. Let's take a look at what's happening in this query. I can see that I am using my non-clustered index. I'm scanning it, however. My non-clustered index simply has a few less pages than my clustered index. There is some small amount of information from the clustered index that I didn't add to this non-clustered index. I have most of the table in this non-clustered index, but not all of it. When we look at what's happening with my non-clustered index here, we can see that we have the same predicates that we had against the table. We're checking, is total name count greater than or equal to 10? And is first report year equal to last report year? They are hidden filters on this non-clustered index. We have not been able to seek on first report year, even though it is the first column in our index. So we have made a very minimal reduction to the logical reads here, because we're now scanning just a slightly smaller structure than our clustered index was. Why isn't this seekable? Let's look at some samples of the data on the index pages to see why this isn't seekable. Our index is built on first report year as the leading key column. Everything is primarily sorted by the first report year. So all the 1880s are going to be together. All the 1881s are going to be together. All the 1882s will be together. And then after that, the secondary sort order is last report year. The third sort order is total name count. Let's take a look at what that really looks like, though. I have here a query that looks at the sys.dmdb database page allocations dynamic management view. And this is a technically undocumented, it's not supported, but it will give me a list of all the pages that I'm using in this index. So I have some SQL in here saying I only want the pages back for the index with this name, and I only want allocated pages in the leaf of the index. I'm running this in detailed mode. If this was a large table, that would be slow, but it's a really tiny table. We just want to look at this as an example. So let's pick a page number. Let's pick 102473, and I'm going to put that into this dbcc page command. dbcc page is also undocumented and unsupported, but we can use it to say for the Babby Names 2017 database, for data file 1, and this was also in my dbcc page output, it told me that the page numbers I'm looking at are in file ID 1. I want to look at this page number, and then we have different options for how the data is returned. This style 3 will return the data to Management Studio in a table. It'll look at that AK page and be like, here's what's on that page. And it gives it to me in this nice table view. For this format to return in 2017, I don't have to use any sort of trace flag. It comes up and shows it to me automatically. I can see my first key in the index here is first report year. And everything, right now I'm in the 70s, I'm in 1973. And here's the 2006s, is what we happen to be at on row 0 and row 1 on this page. So here is the, these are first name IDs whose first report year was 1973. For this one, the last report year was 2006, same for the next one. And then for this one, the last report year, it lasted a little bit longer. The last report year was 2007. But imagine trying to seek on this index for, I need to figure out where 1973, where the last report year was also 1973. Now it would be before this in the index. And if I did have a query that said where first report year is 1973 and last report year is 1973, we could seek to those rows. But they would then be among other rows where, right after that, where first report year was 1973 and last was 1973, we would then have a bunch of rows where last report year was 1974. So if we wanted to do this for all the years in the table from 1880 to 2017, we would have to be, okay, I want to look at where 1880 is the first report year and 1880 is the last report year. I'd have to seek on those, and then I have to go back out. Okay, 1881. Okay, 1882. Have we provided SQL Server with a list of report years? No, we haven't. We have simply said we want them to be equal in our query. Even if we did supply SQL Server with here are the exact report years we want you to seek on in the table, doing this for every year individually from 1880 to 2017, would that be wise? Wouldn't it be less work to do what it's doing and simply say, okay, I'm just going to scan these pages and then do the comparison as I go, because the results that I'm looking for are all mixed up throughout the table. I have 1880s here and 1881 and so on mixed up throughout the table. Because SQL Server is pretty good at scanning things efficiently. So this index is, while it's seekable for individual values for first report year and last report year, when I am comparing the two columns in a query, that is not seekable in the same way that comparing a column to a scalar value is seekable. It is a whole different ballgame comparing these columns to one another. Looking at sometimes, I don't always do this with dbcc page and look at the page on the index, but sometimes thinking through sample data, looking at my index definition and thinking through, okay, what will this index really look like if this is my first key in sort order, this is my second key, and so on. That helps me and to picture it. And if you want SQL Server to help you picture it, you totally can with a test system figuring out what is a sample page in the leaf of this index. And then we can see the keys in the index. We can even see that first name ID has been secretly snuck into our index because it's the clustered primary key. And we do have an included column of first name here. And I always enjoy looking at the names that happen to be on the page that I pick out of here. Canada. We have the first name Canada. There's always so much interesting stuff in there for fellow name nerds like me. Well, that was our first index. Our logical reads right now are at 448. I think we can do better than that. Let's do a little better than that, because we have just seen that these two predicates, first report year and last report year, that it's not seekable to just say this column is equal to that column. However, we have another predicate to think about. The total name count column is looking like the most seekable predicate we have in this query, even though it's an inequality, and even though it's going to be a lot of names in our database. We don't get names reported in this data set unless there are at least 5 babies with that name for a given year. So saying that we only want rows back where there is more than 10 names, that's not going to eliminate a huge part of our data set. That'll eliminate some, but we should be able to seek if we put total name count first. And it may also help out the order by in our query to pre-sort the data by total name count, so we at least can get some seeking into the query. This time, I have simply changed the order of my key columns. I've put total name count first, and I have put descending there. My order by is descending. It is optional for me to put descending in there, even though the query is using descending. If I create an index ascending, SQL Server does have the option to figure out which way it wants to perform a scan. There are a few limitations in certain situations. I am, in this case, trying to tailor things to the query. So I have said total name count descending, and I have left first report year and last report year in my key. Now, based on what we've already seen, these are not going to be seekable, but I just want to prove it to you that even if I put them in there after total name count, we are not magically going to get a seek out of these columns. Let's see what our baseline is comparing to now. We are now at 339 logical reads. We started out at 482. So we have made some progress now. And looking at my query, I do get an index seek. When you see the word seek, it doesn't mean that it's necessarily the most efficient seek in the world. It may be the largest tooltip in the world, though. This tooltip likes to be just huge for this table. And I think for convenience, we will go ahead, since the tooltip is just taking over the screen, we're going to go to the properties window for the index seek so that we can see the seek predicate in a more readable way. I'm going to click on this button to pop up the seek predicate. We are seeking on that leading column in our index only. Once again, we are not seeking on the first year reported or the last year reported. We are seeking on total name count and saying it needs to be greater than or equal to, it's taken my number 10, which was put in the query as a literal. It has automatically parameterized it, and it ended up not being the type that it wanted. It's saying, oh, this column is a big int. The value I'm comparing it to, I should also make that a big int before I compare it. Just a very small amount of overhead because it's performing the conversion on the literal value that I passed in, which it's auto parameterized. Kind of a lot of detail packed in there. But the big picture is we are not getting a seek on first report year equals last report year. That is, once again, in a predicate, also known as a hidden filter, it's having to check every row for that. It's not able to seek to them. And since they are not seekable, they are really not adding value while being in the key of our index. What they are doing by being in the key of the index is making the upper parts of the tree, not the larger parts of the tree. They're making root and intermediate pages of the key of the index have to contain more data, because all of my key columns only are what are in my root page and intermediate pages. If I don't need columns to be in my key, I shouldn't put them in my key, because if I can't seek on them and ordering by them isn't providing me any value, I may as well include them in the leaf of my index so that the upper levels of my index are as lean as possible. If there were other queries who would benefit from having them in the key of the index, that would be a consideration. We are pretending we are in a vacuum here. We are indexing simply for one query and learning, okay, if we wanted to make things as good as possible for this one, what do we get? So I am going to go ahead and drop this index and now move them into the included columns of the index, because if I cannot seek on these and if I don't need them to be ordered in the index, they are not providing me with value by being in the key. They're just adding baggage to those upper levels of my index. I have now an index where total name count descending is the only key column I have, and I have included first name, first report year, and last report year. Measuring this now, our logical reads is at 338 logical reads. We saved one logical read. Now, admittedly, this is on a small scale. This is a small index. We saved one little bit by not putting that column in the key. If it was a larger index, there would be more intermediate pages if we had more keys in there, and we might save a few more logical reads. This is definitely an incremental savings, but if our goal is to get logical reads as low as possible, it counts, and this is one logical read less for the query. Well, if we are measuring by logical reads, we could make the logical reads less by also compressing our index. This is more about adding on to our index design. This is more about putting spoilers on the car that we have designed here rather than true index design. But it is the case that if we compress the index, we are trading off CPU for I/O, because if we use here data compression equals page, each page in my non-clustered index will be compressed down, and we will have to decompress it when we're going to read it, but our index will be smaller. We will still be able to seek on total name count, but the pages that we read in that seek, there will be fewer of them. Now, we're measuring only by logical reads, so this is valid. I create the index, and now when I run the query, I do have only 183 logical reads because my compressed index is significantly smaller than the non-compressed index. Looking at my execution plan, I'm still able to do that seek. I still have the world's largest tooltip, but if I look at my properties window, I will see that my seek predicate remains the same. I'm still seeking on total name count. I still have to check every single page after I've decompressed it. I have to say, okay, is first report year equal to last report year here? But my overall logical reads are absolutely lower because I've compressed the index and made the logical reads less there. These are the sample solutions I have for you for the level 1 of this challenge. Next up, we're going to look at how we can use some fancier indexes to drop those logical reads even lower.